Hello everybody. The last time that we discussed the basic information regarding the mechanics of materials. Last time that we discussed the three conditions that we have to use for any analysis in structural systems and also solid mechanics systems. So today, starting from today, and we're gonna talk about the real problems. The first topic that we want to talk about is mechanics of materials, actually loaded members. Basically, these are one-dimensional problems. Today, I found in this morning there is something wrong with my camera. That's why I cannot show you my face in this lecture. The probably is okay, yeah. And here today we're gonna use the lecture note, the PDF lecture note, and then my iPad for my handwriting. Okay, the first one in this section is the outline. So here the learning objectives is, as I mentioned, we want to talk about one-dimensional problems. Here we want to talk about how to measure the changes in length of actually loaded members based on the force displacement relations. And then we want to talk about so-called support reaction. In 우리말 we call it 반력. And then statically indeterminate bars. The statically indeterminate means 부정정. And then the opposite meaning of 부정정 is 정정, statically determinate. The difference between the statically determinate or statically indeterminate is if we can determine the reactions by using only the equilibrium condition, then we call those structures statically determinate structures. Okay, so if you finish our analysis so without using the comparability condition, then you may consider the structure is statically determinate structures. And then also here in the third topic is very important to understand the overall configuration of the analysis. Is here we have certain strain not caused by the stress. So we have other strain contributions coming from the temperature change and misfit and also the pre-strain effect. So we intentionally introduced the pre-strain effect. Have you ever heard about pre-stressed concrete? Pre-stressed concrete. In English, the pre-stressed concrete. Okay, so in abbreviation we call it PSC concrete. And then here also we want to revisit the arguments of normal and shear stresses on inclined section by using the equilibrium condition and actually loaded parts. And then here these two are advanced topics that we will discuss what aspect that we have to consider if we have any holes in our structural members. And then also we'd like to talk about the concept of strain energy, the energy concept, and this is very important, the energy concept. And actually here I prepared a separate the subsection for the deformation energy. And then I will introduce the concept of fatigue and nonlinear behavior also. 현진이, basically I'd like to organize this class in online lecture in this semester. Okay, so let's consider the simplest one-dimensional problem, a spring. Say I have a spring whose length is measured by capital L, and then the here left hand side is fixed. Okay, so at this moment let's forget about any coordinate system. So in the first section, I emphasized you several times that we have to introduce a coordinate system before any analysis. Okay, but here we will talk about the concept of one-dimensional analysis, and then this is kind of analogy of our system. So let's consider this spring only. So if you apply a force to the end of this spring, then we must have certain kind of elongation. Here the load is measured by P here, P, capital P, and then we have elongation. Okay, so if we apply the load away from the spring, then the spring elongates. And then if you do the opposite direction, then the spring shortens, isn't it? Let's consider the linear elastic system. If spring is linear elastic, then the load P is linearly proportional to the elongation, isn't it? So we can introduce a proportional coefficient to this proportional relation, K delta. This is called spring modulus. Okay, the spring modulus is defined as apply load P divided by delta. Another way we can define the compliance. Compliance in this problem, it is defined as inverse of the spring modulus. This is delta divided by P. The physical meaning of spring modulus is this. Okay, this is always important to understand the physical meaning of an equation. The spring modulus is a force, okay, a force caused by unit elongation. That is the spring modulus. You understand? Basically, that represents the slope. If you plot the load P elongation together here, we must have a linear relation. So if you measure the spring modulus for the unit elongation, and then we must have this, the force corresponding to unit elongation in this spring. And then we do the same thing. For unit load, okay, for unit node, if you can measure the corresponding elongation. This is compliance. Does it make sense? Okay. And then depending on authors, sometimes we call spring modulus or the spring stiffness. Okay, for this simple one-dimensional system, both terminologies mean same. Okay, for this one-dimensional analysis, we have certain requirements. So first, we need to consider straight members in the longitudinal direction. Okay, in longitudinal direction, we want to consider straight members. And then I want to consider a constant cross-section. Okay, constant cross-section. The cross-section can be a circular or rectangles, or you can consider hollow tubes, and then a thin-walled open sections, and this is called I-shaped sections. Okay, I-shaped section. In 우리말 I형 단면. And this is called channel section. This is called 원형 단면, 사각 단면, 튜브, 뭐 이렇게 부르는 거죠. So as we discussed last time, for any analysis, so we always consider three conditions always. The first one is equilibrium. In these simple problems, we can calculate the stress by using this equilibrium equation. So if you divide the load by the cross-sectional area, then we can obtain the normal stress. And then the compatibility, we can measure the strain by dividing the elongation by the length of the member. I can calculate the strain value. And then between the stress and strain, there must be a constitutive relation. So if you use Hooke's law, the stress is proportional to strain. The proportional coefficient is given by the elastic modulus. Okay, let's plug in the stress here and then strain here. Then we can easily obtain, okay, look, say stress is equal to the elastic modulus and strain, and then in this lecture note we have stress is equal to P divided by cross-section area, and the strain is elongation divided by the length. Okay, let's plug in here. Then if you plug these two relations into the first equation, then you have P over A is equal to elastic modulus times elongation divided by the length. Alright, so let's rearrange this equation with respect to elongation delta. The elongation delta is given by elastic modulus and cross-section area and length and applied load P. And then we can find some kind of analogy. Can you find this? So let's compare this spring problem. In the spring problem, when we calculate the elongation of spring, we multiply the load P to the compliance, isn't it? Okay. Here we can find a similar relation here. So this is called compliance. Okay, this is called compliance. In 우리말, compliance means 유연도 계수. 유연도 계수. Alright, let's rearrange that equation with respect to load P. So if you do that, the P is equal to EA over L times elongation. So if you compare this equation with this, that we formulated for one-dimensional spring, here we can find the left-hand side load P and the right-hand side elongation, and then the proportional coefficient, the stiffness, isn't it right? Stiffness. Here the stiffness, K. The stiffness in 우리말, 강성도 계수. Or simply we call just 강성, okay, 강성. So make sure that 강성 is different from 강도. And if I translate to English, the 강성 is translated to stiffness, and 강도 is translated to strength. Okay, they are different. Okay, so although in Korean we have 강성 and 강도, only one character difference, but these are completely different from each other. Alright, so now let's talk about the real problem. So before we talk about real problem, so let me revisit this spring problem again. Okay, so in this formulation, so we didn't discuss the internal forces yet, isn't it right? So now let's consider the internal forces. Okay, so if I have spring, and then it's loaded by force P. So now I want to do any analysis. So this is, if I want to do that, then I need to recognize what is external force. So this is external force, isn't it right? This is external force. And then do we have any reaction? Yes, we have reaction. This is called reaction. Isn't it right? So now before we start any analysis, I want to define a coordinate system. So I want to consider the right hand side is positive x direction. So here, if I want to consider any the force equilibrium, sum of all the forces in positive x direction should be equal to 0 according to the force equilibrium condition. So since we are using this coordinate system, the force component, the magnitude of force vector, the external force vector is what? P. This is plus P because of the choice of this coordinate system. So what if you choose this coordinate system? If you choose this coordinate system, then instead of P we have to write minus P. Is it clear? Okay, so everything depends on the choice of the coordinate system. And then P plus the reaction. So make sure that reaction is unknown. Okay. And that this should be equal to 0. That's why here we can calculate the reaction. The magnitude of reaction is minus P. So now I want to consider a free body diagram. So let's consider this free body diagram. Alright, so omega 1. So if you do that, to satisfy the force equilibrium condition, if you consider only this, okay, this is omega 1, okay, omega 1. So if there is no internal force, we cannot satisfy the force equilibrium condition. That's why we can conclude that there should be internal force. Let's consider internal force. What's the sign convention for the internal force? Sign convention for the internal force is what? Do you remember the last time I told you that the internal forces are nothing but the stress resultant? That's why the sign conventions also follow that of the stress. That's why if it elongates, this is positive. That's why this is our default internal force. Here the N is internal force. So note here P is this external one. Okay, this is omega 1. Okay, so can you calculate the magnitude of internal force? So if you consider the force equilibrium, the magnitude of internal force is equal to force P. So now I want to consider another free body diagram. Let's consider free body diagram 2. Omega 2. Okay, so if you consider omega 2, then I already calculated the N here because we cut here now in omega 2. That's why we can easily recognize that the force, internal force on the right hand side of omega 2 should be equal to N. So now we are ready to replace this equation, P, by the internal force. So instead of writing here the P is the magnitude of external force. So now a better way is what? Instead of external force, to define the stiffness, I want to use internal force N and the elongation. Okay, and then compliance, and then elongation divided by internal force. This is better, isn't it? And also, I'd like change this equation too. Instead of actually in many textbooks it's written this way, so PLEA, but it is confusing. Okay, so make sure that here force P is certainly to measure the external force. So instead of this, the reason that I'm doing this is what? Look at the left hand side here. Delta is elongation, not the displacement, isn't it? So instead of that, so I'd like to correct this equation in this way. the elongation delta is equal to the internal force N times length EA. Okay, that is better, more straightforward. This is equal to LEA and the internal force. The N, internal force N is elastic modulus and cross-sectional area divided by the length and then elongation. And this equation is better, so it provides more information. Do you have any questions up to here? So now I want to consider the real problem here. Okay, so I have a bar, the real bar, and then if I look at the right hand side, and then I have a concentrated load here. Because of this load, there must be some elongation. Okay, so before any analysis, so we want to introduce a coordinate system. Otherwise, we cannot start our analysis. This is my problem. And then, as I told you, we have a reaction here. Okay, reaction. And then let's define a coordinate system. X. This is choice 1. Okay. Case 1. Then if I do that, so if you use the force equilibrium for a whole system, so R is equal to minus P. So what does it mean? Actually, the reaction is working in this direction because of minus sign, isn't it? And then let's calculate the internal force. So I want to consider the cross-section area, by the way. So look at this. So force equilibrium, and then stress, and strain, and displacement. So we are taking this flow, okay? So now let's calculate, here we just calculate the reaction, isn't it, right? The next step, we need to calculate the internal force. So let's consider this free body diagram. So if you do that, I have an external force P. And then according to the sign convention of internal force, if the any internal force stretches the member, then this is positive default, isn't it? So I want to consider positive default internal force N. So if you apply the free body diagram for this small segment, then I can easily calculate the N is equal to P. So make sure that the magnitude of internal force is equal to the magnitude of external force, not the vector, okay? Not the vector. So once I have this, then are you ready to calculate the stress, right? Because the internal force is nothing but the stress resultant, stress times the cross-section area. So now we can calculate the stress value. Stress is equal to, let's plug in this relation here, then the P divided by the cross-section area. So now we are here. So now let's calculate the strain value. Strain is by Hooke's law, the stress divided by the elastic modulus, isn't it? So let's plug in here. Then elastic modulus and cross-section area, and then load P. And then what's the next step? So we just calculate the strain value. What's the next step? Then we need to calculate displacement. So make sure that the force is a vector, and then the displacement is also a vector. That's why, before we calculate any displacement, I need to choose where we calculate the displacement. So let's consider this is point A and then point B. So I want to use these two displacement vector because I'm using this coordinate system. So I want to consider the default direction. This is a default direction. Okay. So now let's try to calculate the elongation. Why? The strain is defined as the elongation divided by the length, isn't it? So let's calculate the elongation. So how do you calculate the elongation? So to calculate the elongation, we need to subtract here UB and the UA. Do we have to subtract UB from UA to calculate the elongation, or we have to subtract the UA from UB? Okay, let me repeat. Option 1. So we subtract UA from UB. Option 2. UA from UA minus UB. Which one is correct? This is option 1. This is option 2. Which one is correct? Please give me your opinion in the chatting window. So I'm calculating the elongation. I'm waiting. Which one is correct? So I want to calculate the elongation. 전윤식, what's your answer? So we want to calculate the elongation. 조기훈, 영우 1. So why do you think option 1 is correct? So 영우 gave answer. So can you explain the reason that you considered option 1 is correct for other students, so that they can understand what you think? So make sure that the elongation, what's the definition of elongation? Elongation is, the way of stretch it, isn't it, right? The way of stretch it. That's why, to get the measure of elongation, we need to subtract UA from UB. So otherwise we cannot get it. So if I want to use the magnitude of displacement vector, so make sure that these forms displacement vector. Make sure that this is displacement magnitude, okay? So because to define a vector, we need magnitude and direction. That's why we need to consider the magnitude UB and its direction too. So here, this is UB minus UA divided by length L. So let's consider a boundary condition. Certainly point A is fixed, which means UA must be equal to 0, isn't it? So we drop UA here. Then finally, I have what? Where is it? Then finally, I have, as a strain, I have UB divided by the length L, and this is equal to what? It comes from here. So P divided by elastic modulus and A. So let's focus on this equation. So if you do that, the external load P is given by elastic modulus and cross-section area and divided by the length and UB. So make sure that this is what? This is the magnitude of displacement vector and the magnitude of external force. And also we can get the nodal displacement at point B in terms of applied load P. You understand? Now let's consider another procedure. Here I noted case 1. Okay, case 1. So instead of using this coordinate system, I want to use another one. How can I change the size? Okay, now instead of using this coordinate system, this is case 2. Second choice. So most of people would use the right hand direction coordinate system, but let's say we have a student who doesn't want to follow other people's option, such that he want to use this coordinate system x. It's perfectly fine. Okay, perfectly fine. But here node P is already given in this direction, but now the direction of reaction, before we calculate, before we check any, the reaction is not given yet. Okay, then because unknown reaction, so we assume the direction of unknown reaction follows the direction of coordinate system. Okay. Alright, so let's check the force equilibrium for whole system unknown. Now I'm using this coordinate system, right? The sum of force should be equal to 0. Then according to this, the direction of reaction is positive, but direction of external force in the negative direction, P. That's why in this calculation reaction is equal to P if I choose this coordinate system. Okay, well, let's compare the result with the previous one. Though you may see, if you check the vector, the result is exactly same. The reaction is heading to the left hand direction. So now let's check the free body diagram as given here. So if you do that, then what? So I have force vector P, and then we wanna consider what? You wanna consider the internal force. Okay, if the member is stretched by this internal force, then its sign is positive, isn't it, right? So that's why I wanna consider this default direction of internal force, which stretches the material. Okay. So here, using the force equilibrium, then the magnitude of internal force is equal to the magnitude of external force P. Same. So let's calculate the stress value. Stress is internal force divided by cross-section area, the magnitude of stress, what I mean. And the strain is what? Strain is stress divided by elastic modulus. That's why elastic modulus, and then internal force, P. So now the strain, please make sure the strain is elongation. The elongation is equal to strain times the cross-section area. This is elongation, isn't it? So here let's plug in the calculation of strain here. Okay. So now the next step is we need to consider the elongation. Okay, because we use this coordinate system, and then now let's calculate the elongation. Okay, again, I'd like to give you another question. So now we want to calculate elongation. Which one is correct? Option 1 or option 2? 오유준, 유준이, 기훈이, 준호, 현진이, 홍현진. Which one is correct? Okay, very good. So in this case, so option 2 is the correct measure of elongation, isn't it? Because this is the direction of my current coordinate system. So now I want to use the option 2. My elongation is UA minus UB is given by EA times P. So now let's check the boundary condition. So UA is equal to 0. So drop it. That's why we can conclude that the nodal displacement, the magnitude of nodal displacement is equal to minus length divided by elastic modulus and cross-section area times node magnitude of node P. What does it mean? So if we consider any node P value in this direction, my nodal displacement follows the minus direction of the with respect to this default positive direction as defined in the choice of coordinate system. So which means the minus sign means my nodal displacement would generate in the right hand direction. Is it clear? So it doesn't matter what kind of coordinate system you want to use, okay? As long as you use consistent coordinate system from the start of your analysis to the end of your analysis, then you would get exactly same result. Now we talked about one-dimensional solid member. Here I'd like to give a note for cables. So cables is typical, one-dimensional members. Okay, it can resist only the tension only. So here, typically, if you compare the deformation of elongation of cable to that of prismatic bar with the same cross section, usually it produces more elongation. Okay, that's why we say that the stiffness of elasticity for a cable is less than the solid material. That's why for the cable we use effective modulus, 유효 강성계수. Okay, not for just material. Here let's consider a simple example. So in this example, I have a spring here. I have spring, and then we put a weight, and then we have a hinge point. Because of this weight, and it produces force because of moment equilibrium, and this force would stretch the spring. And then we need to calculate the movement of point C. That's the problem. Okay, first I want to calculate the force at point C. Okay. So I have frame and hinge. So I have a weight here, W. And its length, arm length is given by B. And then here, the height of the lower part is given by C. Okay, so before any analysis, we need to introduce a coordinate system, isn't it, right? Otherwise, we cannot do that. So X and Y. So let's use this two-dimensional system. Because of this two-dimensional system, so I'd like to assume the force reaction at point C in this way. Okay, so let's consider force at point C. So if you do that, let's consider force equilibrium in the vertical direction. If you consider the force equilibrium in the vertical direction, so we can easily recognize at hinge point, we must have a reaction. The reaction in the y direction is equal to W. And then also let's consider the force equilibrium in the horizontal direction. Then also we can recognize the magnitude of reaction in the x direction is equal to minus Fc, isn't it? But using this, we cannot determine, the value of Fc. That's why let's consider the moment equilibrium. So moment equilibrium, so with respect to the hinge point, this is equal to 0. So if you do that, the moment produced by the weight is W times B, because force times this arm length, isn't it, right? And then Fc times Fc times C should be equal to 0. Then we can calculate the magnitude of Fc very easily. This is equal to minus B over C and W. This is the magnitude of Fc. Then now we can focus to the spring. So now let's focus on the spring here. Okay. Then let's focus on the spring. I have a spring here, and then the spring is attached to point C. So according to our calculation, the direction of Fc is what? Not in the right hand direction, is to the left hand direction. Its magnitude is equal to BCW, isn't it? Okay, there must be force equilibrium at a cross section too. That's why we need to have exactly same force, B over C and W. Okay? So now let's solve the problem. So let's consider support here. I can calculate the reaction very easily. So that's why I don't want to repeat here. The elongation at that point is what? The length of the spring divided by, So we have the spring modulus, 1 over spring modulus, and then the force W. This is elongation. Okay? Alright, here let me stop the first part of my lecture. So we'd like to take around 7 minutes break, and then we will do the second one in 11:20. Okay, in 11:20.